All right, section 3.5. It's the last one of chapter 3. Here's what we're looking at. Since it's talking about rational functions, we better know what one is. Asymptotes. And then how do you graph these things? This is probably the last real hardcore graphing we're going to do. We'll look at graphs of other things later on, but in terms of us graphing it, this is probably going to be it. So today, we're talking about those first two. So the question comes up, what is a rational function? Function. Rational, we know that when we talked about rational before, it means you can make a fraction out of it. It means the same thing here. It's just a little more complicated, as you might expect. So it's a function in this form. And the numerator is a polynomial function, and the denominator is a polynomial function. So I might have x squared plus 6 on top and x minus 7 on the bottom, something like that. And finally, an important thing to notice here is that the denominator can't equal 0. Well, that makes sense. So you can't plug a value in for x that will make that denominator 0. Otherwise, that function would be undefined. All right, so that's what a rational function is. Here's the simplest kind we got. You don't have to copy this down. Just take a look at it. The function is 1 divided by x. Now, these graphs are going to get weirder from what we've seen before. There it is zoomed in. Here it is zoomed out. Same function. Notice something about it. It looks like, let's start out there. As I go toward negative infinity, as I'm going this direction out here, that graph is getting closer and closer and closer to the x-axis, but it's never going to touch it. As I'm going in this direction toward positive infinity, same deal. That graph is never going to touch the x-axis. It'll get closer and closer and closer. And then as I get closer to 0, say from this direction, the graph is never going to touch the y-axis. And as I get closer to 0 from this direction, the graph is never going to touch the y-axis. So that graph is being hemmed in by the x-axis and the y-axis. Okay, that's the simplest polynomial rational function we've got, I think. Because on top, really, it's f of x equals x to the 0 power over x to the first power, right? It is a polynomial on top. X to the 0 power is just 1. All right, let's keep going. Brings up, what's an asymptote? We're just talking about asymptotes today, really. We'll save the graphing for another day. like tomorrow. Good face. Bless you. Turns out, here's what it is. Now, I should add something here, just to make it clearer. This is as the absolute value of x approaches infinity. So as x is getting closer to positive infinity, or as x is getting closer to negative infinity. So I probably ought to put plus or minus out here. No, I'll leave it just like that. Okay, so as we go toward positive infinity or as we go toward negative infinity, this graph gets closer and closer to an asymptote but never touches it. Now, it might cross it at some point. We'll look at an example of that. We got 3 different kinds. Horizontal, that's the way the x-axis was in our 1 over x example. We've got vertical ones. That's what our y-axis was in our simple little 1 over x. And then we've got these oblique ones, which is just a slanted line. But these asymptotes are all straight lines, notice. Horizontal, vertical, or slanted. Let's take each one of these one at a time. Vertical asymptotes. The lines are going up and down. First off, the graph could have more than one, it could have one, it could have none. So it might not have any, it might have just one, or it might have several. Now, in our little 1 over x example, it just had one. It just had the y-axis. That was the only vertical asymptote it had. Okay? Let me make this a little more clear. It can't intersect, the graph can't intersect a vertical asymptote as you get out there toward infinity or negative infinity. It might before then, but the further out on the x-axis you go, it can't. It can never touch it at all. So how do you find these vertical asymptotes? First of all, look at the denominator, set it to 0, and then solve for x. So we're just concerned with the denominator here for our vertical asymptotes. Get the denominator, set it to 0, solve for x. So let's say I set the denominator to 0, I get x equals -1 and x equals +6, something like that. I know I would have vertical lines at -1 and +6 that are going to hem my graph in. That's all that's saying right there. So let's look at this example. So f of x, on top I've got x plus 3. On bottom I've got x squared minus 1. I want to know, how do you get the vertical asymptotes? So first thing I do, I set the denominator to 0. And I solve for x. And I'm getting x equals plus or minus 1. So I know what? I know I've got vertical asymptotes at positive 1 and negative 1. And again, these are just the vertical ones we're talking about. We can have vertical, we can have, well, we'll talk about horizontal, or we might have oblique. Okay, so here's what that looks like. Here's a picture of what we just figured out there. Our function's in red. I've got a blue asymptote over there at negative 1 and green at x equals 1. That's it. I mean, we just found the vertical asymptote. So what does that mean? It means as I go further out, as I get closer to 0, if I'm approaching 0 from this direction, as I'm approaching x equals 1 from this direction, the graph's never going to touch it. As I'm approaching it from this direction, the graph's never going to touch it. There's always going to be a gap in here. Always going to be a gap. And same way for my negative 1 asymptote. As the graph approaches it, whether it's up here or down here, never going to touch. Okay. Let's talk about the horizontal ones. That's all there is to finding the vertical ones. Set the denominator to 0, solve for x. Horizontal. We have two situations. Here's the first one. So the first thing you look at when you're looking for horizontal asymptotes, look to see if the degree, now we're talking about the degree of the numerator and the degree of the denominator. If the numerator's degree is smaller than that of the denominator, then the x-axis is a horizontal asymptote. Was that true with our little simple example? This one. Look at the degree of the numerator. It's 0. The degree of the denominator is 1. Was the x-axis a horizontal asymptote? The answer is yeah. Look at the denominator. If I set the denominator to 0 and solve for x, well, it's already solved. There's a vertical asymptote. What's x equals 0? That's the y-axis. So these rules are holding even with this little simple one here. Okay. Here's an example. This is the same function we just looked at in our vertical asymptote problem. Notice I've got the little blue vertical asymptote at -1 and the green at +1. Now notice something. And this came up during period 1. It's easy to see out here as we're going toward positive infinity go in this direction, that graph is never going to touch this x-axis asymptote. By the way, how did I know it was going to be there? Look at the numerator's degree, it's 1. Look at the denominator's degree, it's 2. So I know the x-axis is going to be a horizontal asymptote. As I'm going toward positive infinity, it's easy to see that graph is never going to touch the x-axis. But look what happened right here. Right in here, the graph crosses the x-axis. You might go, okay, well then the x-axis is not an asymptote. Well, yeah, it is, because as we're going out this direction toward negative infinity, it's never going to come back up and touch. So it can cross back over here someplace. But once it does, it can never get back up to it. And something similar might happen on the right-hand side of a different function. It might dip below it, and then it'll never come back up. That sort of thing. These graphs are going to be weird. Okay, that's the first situation for a horizontal one. If the numerator's degree is less than the denominator's degree, then the x-axis horizontal. Here's the second situation. I'll give you a second to copy that down. Now this is saying, again, talking about horizontal asymptotes, if the numerator's degree is the same as the denominator's degree, you look at what? You look at the coefficients of the leading terms and just make a fraction out of them. So if the degrees are the same, you look at the coefficients of the numerator and denominator's leading terms and just make a fraction. Check it out. For the numerator here, I've got 3x squared. For the denominator, I've got x squared. So those degrees are the same. Forget the rest of it. The degrees are the same. So what do we do? Well, I know in front of the x squared in the denominator, there's a 1, right? So I make a fraction out of this 3 up here on top and the 1 on the bottom. Okay, 3 divided by 1 is just 3. Well, look where the horizontal asymptote is. Sorry. The horizontal asymptote is at y equals 3. And notice again, the graph might cross it right here, but as we get further and further toward positive infinity, it's never going to touch it. And as we get closer and closer to negative infinity, it's never going to touch it. So it's a true asymptote. Making sense? For a horizontal asymptote, either the numerator's degree has to be less than the denominator's, or they have to be the same. By the way, do we have a vertical asymptote here? I'm not seeing one. How come?
Because the bottom and top have the same degree.
No, sir. How do we get vertical ones? It would. Good answer. I take the denominator, I set it to 0. So I'm getting x equals plus or minus the square root of negative 1, which, as the lady says, imaginary. That's why we don't have a vertical asymptote here. So if I just gave you that function and said, find all the asymptotes, There's only going to be one. That's that horizontal one. You'd say there aren't any vertical ones, there aren't any oblique ones, there's just that horizontal one. Good answer. Let's take a look at oblique ones. Oblique means slanted. And again, we're basing all this on just an equation, just a function. Again, we're looking at the degrees. This is saying if the numerator's degree is 1 bigger than the denominator's degree, well, we're going to do something. What do we do in this case? Gets a little more complicated. We divide the numerator by the denominator. We're dividing one polynomial by another. That can get kind of yucky. But we do have synthetic division, so it's not going to be that bad. And on a test, I wouldn't give you one that's horrible anyway. Then what do? We throw away the remainder. We just ignore it. Easy to do. Then what? Whatever's left of the quotient, whatever's left of that answer we got when we divided, that's the equation of a straight line, and that's going to be our oblique asymptote. Let's take a look at one. So I've got a function here. On top is 4x squared minus 2x plus 1. On the bottom is x minus 6. Now I'm looking at that. The degree of the top is 2. The degree of the bottom is 1. So I know I've got an oblique asymptote. Let's do some synthetic division. So I set it up like this. No need for placeholders because it goes x squared, x, and then a positive 1. And I divide, and I'm getting this. So now I toss the remainder, and I get this from my oblique asymptote. Because this right here is really 4x plus 22 that we have left over. We're taking our leftover part here and just making a little equation out of it. Y equals that. Let's take a look at what it looks like. In red is our function. There is our slanted asymptote. And its equation is y equals 4x plus 22. Now that's zoomed way out. Looking at this right here, do I have a vertical asymptote also? Yeah, if I take the denominator and say x minus 6 equals 0, x equals 6, then that means cutting through here someplace. That's right in here. It's going to go all the way up. I've got a vertical asymptote at x equals 6. Notice that function's being hemmed in by those two asymptotes. That's going to help us graph these things because we'll just get a few points on the function and then we'll use the asymptotes to sketch it. Does that look like that's symmetric, the function? Not around the origin, it's not, but it looks like it's symmetric around some other point. So let's just work a couple of problems here. 3 to be exact. How about finding all the asymptotes of this function, please? I'll be doing the same thing. See if you all agree. Here's another one. Oh, this is what it looks like, by the way. Kind of weird. Notice the blue line is the x-axis. That's our horizontal asymptote. And as I go out here toward positive infinity and toward negative infinity, our graph is never going to touch. And our 2 green vertical asymptotes, it's never going to touch there either, no matter which direction you're approaching those asymptotes. All right, here's another one. Please find all the asymptotes. Okay, just to make sure, to get the vertical, I set the denominator to 0 and solve for x. So I've got a vertical line at x equals -1. I'm looking at the horizontal ones. I know the coefficient out in front of this x is a 1. So I'm just taking the coefficients and dividing them. Since the degree of the top is 1 and the degree of the bottom is 1, I just divide the coefficients. And I get y equals 4 for my horizontal. No oblique ones. Here's what that graph looks like. So this vertical asymptote is x equals what? -1? Functions being hemmed in by those asymptotes. Let's take a look at one more. See if I did my math right. Vertical, set the denominator 0, solve for x. Got that. Horizontal, it doesn't fit either situation. The degree on top is 2. The degree on the bottom is 1. So the top is bigger than the bottom. So I know I don't have any horizontal asymptotes. Oblique, I divide the top by the bottom. Notice I'm leaving a placeholder here. Do my synthetic division, throw away the remainder, I get y equals x plus 2. The equation of a straight line. Let's take a look at the graph. All right, so there's several examples just to let you see how it all works.